Well, good morning again. Today we are looking at 11.4. This is page 887 in your textbook. And we're doing something very, very new today, and this is something called logarithms. And logarithms are what are the inverses of an exponential function. And there are two. There's what's called the common logarithm, and you will see this just as log. And on your calculator, if you see your calculator, here's the word log. And that is going to be what's used for the logarithm. Remember, that's the inverse of exponential, which is this button. That's how you get exponents. These two are inverses, and inverses, remember, undo each other. For example, multiplication is the inverse of division, and vice versa. Adding and subtracting are the inverses. Well, exponents and logarithms are the inverses of each other. And then there's another type of log called the natural logarithm. And on your calculator, this will be ln, natural log. And that's a little bit lower on your calculator, right under the log, ln. This is the natural log. And the natural log is the inverse for this little letter right here, e, or it's also over here, e, second divide. And we've used that a few times. Remember, e is used when we want to find compound interest continuously. And we can inverse that by using natural logarithms. And the reason it's natural is because e occurs in the world with population growth, etc. So those are the two types of things today. And we're going to be working with logarithms, which means we are going to undo unknown exponents. Like if it's 10 to the power of x, or 2 to the power of x. We can find the x value when it's an exponent by doing the inverse, which is called a logarithm. So that's our goal for today. So flipping over on 888, we can see the exponential graph of y equals 2 to the x power. And I told you guys already in class that you should have these three values of x, hopefully known as your parent table. We said an input of -1, so anything to a -1 power becomes 1 over the base. Notice our base is 2. So these are our outputs. I'll do that in red here. These are our outputs that we care about. Anything to the 0 power, 2 to the 0 power is 1. Anything to the first power is the base itself. Here's our base. 2 to the first power is 2. And these extra points here are just there to help us on the graph, but the ones that we ultimately care about are 0, 1, -1, 1 over the base, which is a half, and 1, the base, 1, the base there. And since it's exponential, we should know that it is forever getting bigger, 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 bigger on all domain inputs. And we have what's called a horizontal asymptote at y equals k. K is always off to the side. Notice there's nothing there, so in this case it's y equals 0. And this is a very good thing to start here. You should make sure that you double check and look these over a few times before a quiz or before a test, which will be, I believe, next week, early next week. But the domain for all exponentials is all real numbers. So domain is all real numbers, and we can also write that this way. They mean the same thing. The range, however, you can see, the range goes from 0, because that's an asymptote, never goes below here, to forever, 0 to infinity. We always have a y-intercept for the parent of 0, 1. There's never an x-intercept because there's an asymptote there on the x-axis. We always have a horizontal asymptote, that's this line here, at y equals 0. I'd put a little star there and say it's always going to be y equals k, your k value. And the reason that's important is because sometimes we change these equations to y equals a, your base, whatever that is, x minus h power, that remember goes right and left, plus k. There's your k number, which we care about your asymptote. That k number is going to take this asymptote and slide it down if it's negative, slide it up if it's positive, and it's going to take the whole graph with it. This is important. We've seen this a few times. The function will increase over the entire domain. If I ever ask you what interval is the function increasing, you write the whole domain right there, from negative infinity to positive infinity. Everything on this graph is always going up, 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 up. And these are called end behaviors. And this basically says, remember, as x approaches negative infinity, y approaches 0. That's just a quick way to write it. And this one says, as x approaches positive infinity, y goes to infinity, and what this means simply is as the x's go to the left of your graph, the y's want to get to 0, but it never touches it. As x goes to positive infinity, which is the right side of your graph, as x's go this way, y's are getting bigger, 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 so they're going to infinity. So this is everything from exponential graphs. And we're going to do everything the opposite now. That's a logarithm. So what you need to hopefully remember is that a logarithm, L-O-G, and this means either log or it could even be natural log, but both of these, remember, are the inverse, undoing, of exponential. Okay, these are going to do the exact opposite. And something very easy to know is that an inverse will always switch the x and the y values. So think about it for a second. If you have an exponential function, and your exponential function, I told you to memorize these key tables, and we'll use y equals 2 to the x power. So that's our exponential function because we have a base to an exponent. If we have a -1 input up here, hopefully remember it's 1. The answer here, the y value is 1 over the base, so this becomes 1/2. If we plug in a 0, 2 to the 0 power is 1. If we plug in a 1, 2 to the first power is 2. So how do I write this as a logarithm? And that's what we're going to figure out next. Well, the logarithm is going to take all the x's and the y's and do what? It'll switch them. So this x becomes this old y, 1/2. And this y becomes the old x, -1. 0, 1 flips and becomes 1, 0. And 1, 2 flips and becomes 2, 1. And this is now written as log base 2 of x. And I guess we can put equals y. And we'll talk about how to write that in just a second. But notice your base 2 is the same as the base for your exponent. They're the exact same number. So basically you'll write the word log, and then you'll put the base that you used to have here. Alright? And then of course we switch the x's and the y's. I'll show you how to write those in just a second. It's very simple to do, but you have to notice the pattern. Okay? So let's do that on this graph right here. What we're going to do is this is the original graph that we saw right here, and we are going to inverse this. Okay, there's two ways to inverse things. You can either, one, take the x's and y's and flip them on your table, or you can graph a line that's diagonal, the line y equals x, we've done this before also, and reflect it. So this becomes more of a geometry situation. But here becomes the line of reflection. All things will reflect inversely through that line, across that line. And what we're going to do is we're going to graph the inverse of f of x equals 2 to the x power. Remember we said inverses are logs, so this equation becomes log base 2 of x. And that will equal our y answer. And so what we're going to do is we're going to take all these values here on our old table and we'll switch them. And we'll go ahead and plot those. I'm just going to take these three right here and plot them. They're the most important ones that we need to know. So right in the middle of our graph, we used to have -1 comma 1/2. We're going to flip it. 1/2 comma -1. Right here we used to have 0, 1. We're going to flip it 1, 0. And then we used to have 1, 2. We're going to flip it 2, 1. We'll go ahead and plot those 3 points and watch what happens to the graph. So here's the point 0, 1. And when we flip it, it becomes right here 1, 0, right there. Notice what happens is it reflected over this diagonal line. It's like I'm taking my book and folding it over, and there it goes right there. The point 1 to the right, 2 up, turned and became 2 to the right, 1 up. So it goes right here. And the point -1, 1/2 flipped and became +1/2, -1. And what happens is now everything flip-flops, and now our graph is going to go off to the right instead of up. And when it went left flat, it's going to go down flat. And now we still have an asymptote, but notice the asymptote that used to be a horizontal one now has become a vertical one. And this is a line x equals 0. This is your asymptote. Okay, so the inverse of f of x equals 2 to x, is that a function? Well, absolutely. And the way you can always tell a function is vertical line tests. Okay, that is still a function. Explain your reasoning, passes the vertical line test. Alright, here becomes all the key parts of any logarithmic function that you'll need to make sure you know, but basically, remember, we just switched all of the old answers. So the old answer, the domain for y equals 2 to the x power was all real numbers, and the range was from 0 to infinity, so now we flip-flop that. Now our domain can't ever go left, so now our domain is from 0 to infinity, but our range goes down and up forever. Even though it's going to the right, it's also slowly going up, 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 up. So our range is all real numbers, or again, we can write it from negative to positive infinity. And if you notice, that's the exact opposite from our exponential. The domain was all real, the range was 0 to infinity, and look, they flip-flopped. And that should make sense because the inverses are the inputs and outputs reversed. Okay? So domain and range. Intercepts. Well, we used to have an intercept of a y-intercept of 0, 1, but now there will never be a y-intercept, but there is an x-intercept at 1, 0. This is an x-intercept only for the log graph. Okay? Intervals of increase or decrease. Well, now, again, we read a graph from left to right. We are still increasing the graph. Just like here we were increasing, we are still increasing. The difference is we never have negative domains. So what we do is we still say the graph is increasing, it's never decreasing, but now the interval is not forever negative and positive infinity. Now it's this domain from 0 to infinity. That hopefully makes sense because we can't have any x's back here. So whenever it asks for interval, it's asking the x inputs that make the graph go up. Well, since you can only have 0 as the smallest x input, we start at 0. Right here, because that's our asymptote. We never really have a 0 for x, that's why it's parentheses. And then we can forever get bigger x's, 5, 10, 20, 30. It's kind of slowly going to make this graph go higher. Okay? It never decreases. Neither the logarithm nor the exponential graph decreases. And then behavior is a little bit different. And behavior, I'll put EB. And that again says as x, normally we say as x goes to negative infinity, but what's the problem? Well, x's can't ever go to negative infinity, so x's can only go to 0. That's the smallest x we can get. So the y's have to do something when the x's go to 0. So look what's going on. Here's my x's, and as they go to 0, right here, where is my graph? My graph's my blue line. My graph's way down here at negative. Well, what about the big x's? As x's go to the right, x's are going to go to the right, right, and they will get forever big. Notice that's forever big here. Y's, what are the y's doing as the x's go to the right? Well, the x's go to the right, so the y's go up higher, so therefore the y's are also going to positive infinity. So this again is something that you should kind of know and look at based off of the shape of that graph. But this is what's called the logarithm function. Okay, it's the exact inverse, which means you switch the x's and y's for the exponential graph. So on the next page, we'll just kind of talk about the situations that are going on, and we'll just talk about it, and then I'm going to tell you how to write these things. What do you notice about the domain and range of exponential functions and its inverse? Well, they switch. The old domain became the new range and vice versa. What about the asymptotes? Well, for exponential, the asymptote is y equals 0. For logarithms, it's x equals 0. They again switch. Everything is going to switch. What do you notice about the intervals of increase and decrease? Well, first off, they never decrease. Of the exponential function and its inverse, well, same idea. The difference is the interval is negative infinity to positive infinity for exponential, increase, and the interval for logarithms is from 0 to infinity. But they're still always increasing. What do you notice about the end behavior? Well, the end behavior basically says that what's happening overall. The end behaviors again switch also for exponential. The end behaviors will go from as x goes to negative infinity, y goes to 0. As x goes to positive infinity, y goes to infinity. That's for the exponential graph, but the logarithms, remember, everything switches. So now these switch with these. So now it's not x going to negative infinity, but it's x going to 0. Y's went to negative infinity. And as x's went to positive infinity, y's also went to positive infinity. So we just took each one of these and flip-flopped it. Again, switching. Everything switches. And this is the important one. How do we write these logarithm equations? Well, I usually like to rewrite this a little bit. I usually like to take this and I like to bring the equation part to the right side of the function. So I'm going to rewrite it. Instead of y equals 2 to the x, I'm going to write 2x equals y. And here's how you write the logarithm function. A little trick. So first off, we are in exponential. And if we are in exponential and we want to go to logarithms, we're going to trace like a block letter L. And what we're going to do is we're going to start like we normally trace a capital letter L, and we're going to go straight through the base. So the base here is 2, so we're going to come straight down here and touch the 2 first. Then we're going to come over to the equal sign and touch the y, past the equal. And then notice we still got to pick up this x at the end, and we're going to kind of come over here and touch it right there. So what happens is now we've made like a block letter L, and that tells me we're going to write the log. So log. Well, what did we touch first? We touched the base first. We put the base down here. And I don't know why they write it down there. That's just where they decide to write it. So it's log, and it's like a subscript, a little small 2. Kind of like when you were doing the square root or cube root. You put a little cube root, a little small 3 up there. Same idea for this. Then, what did we touch after that? We went over here to, this is called the argument, y. And we're going to put the y answer next, equals x. So this is how you would typically write that. Okay, and if you wanted to go backwards the other way, from log to exponential, well, if we're in log, now what we're going to do is we're going to trace the letter E to go to an exponential. And we always start at the base. Here's my base. So I'll show you real quick. This is the correct answer for how to write it. But what if we wanted to write it the other way? Well, I'll rewrite it so you can see it. Log base 2 of y equals x. So how do we write it the other way? Well, like I said before, we always start at our base. So our base is 2, so we're going to write the 2 first. And then we're going to trace the letter E. So from 2, we're going to go over to the equal sign. And there's kind of like our E. It looks kind of like a cursive E. So 2, then what did we touch? We go past the equal sign always. X power, and then we came around and grabbed the y, so equals y. That's exponential. So if we're going from exponential to log, we trace an L. If we go from log to exponential, we trace an E. And notice we always put the equal sign on the right, so that way we can make our L and make our E. So if it's ever written this way, just flip it so the equation equals is on the right side of the problem, and then you can switch them back and forth. Okay, and then everything, remember, for this graph changes. I also want to show you something really, really important on the calculator. If you went to y equals, you can always type in 2 to the x power, and we can see what our table is. And here we have our key points, 0, 1, 1, 2, negative 1, 1/2. And how do we do the inverse? Well, we can't just hit the log button, because that's okay, that's allowed to do. But if you actually hit the math button, it will help you do logs in any base. And if you hit math, I'll do it one more time, math, and then up twice, you'll see this word log base. So hit enter, and notice now we can put the little 2 down there, and then we come over here and put our x here, and now this is log base 2 of x. And watch what happens when we hit our table. Notice that at negative 1, we no longer have an answer. Well, that should make sense, because remember our graph went down and forever up. You can look back at your graph if you need to. But more importantly, negative 1, 1/2 is not part of our graph. It's really kind of hiding in here. It's 1/2, negative 1. But we'll look at that in here in a second. 0, 1, when you switch it, turns to 1, I'll go over here to the red side, 0. There's 1, 0, which is the inverse of 0, 1, because remember they flip-flop. 1, 2 inverses to 2, over here, 1. So you can kind of see that it does work. And if you graph it, here's our exponential graph. And here comes our logarithmic graph. There it is. And it doesn't really graph all these coming down, but it does go down forever. The reason it doesn't is because they get so tiny, like 1/2, then a quarter, then an eighth, then a 16th, then a 32nd. It gets so tiny that the graph doesn't even really show up there, but it does theoretically go down, 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 down forever, never crossing the y-axis. Okay. So what I want you to try to do is get practice with writing those. So let's go to a clean sheet. I'm just going to come down here at the bottom. This is exactly, let's see, they don't really show you all of these. They just kind of show you this. What you need to know is how to write these. So let's say we take some of these situations. All right. We're going to go on, we'll do B here first. 16 equals 4 squared. Well, how do we rewrite that? Well, let's rewrite that as 4, I'm going to write it down here. This is part B. 4 squared equals 16. Remember, I always like to write it on the other side. So the first question is this exponential or logarithmic? Well, it's exponential because there's an exponent. All right, so we're going to change it and write it into logarithm. 4 squared equals 16. We want the inverse. All right, So what we're going to do is we're going to come trace the L, because the L is the inverse logarithm. So we're going to trace the L like that. Well, we touched 4 first. So we're going to write 4 as our base. Then we touched 16. So we're going to put 16 here. That's called the argument. And then we're going to put the equal sign, and we touch the exponent 2 last there. Notice if we went backwards, exponential, we'd start at the base, 4, trace the letter E, squared, equals 16. 4 squared equals 16. These are inverses of each other. Okay? This means if 4 is squared, you get 16. This is saying log base 4 of 16 is 2. This means if you took 4 to the second power, you'd get 16. So how did we get 16 in log base 4? We did it 2 times. This becomes our exponent. Notice this is always our exponent answer from before. And this is important when we don't know the x. If it's 4 to the x power, we can do this. And I'll show you how to do that a little bit later as well. Okay? How would we rewrite, oh, by the way, here it is, 2 equals log base 4 of 16. That's the same exact thing we did. I just didn't put parentheses. And I always like to put the equals on the right side because then I can trace my e's and my l's. Okay? This is the important one, though, the generic form. Y equals b to the x. Let's do that one now. So on part A, if we have y equals b to the x, I'm going to rewrite it as b to the x power equals y. B is our base. We're going to change this as log something. So it's going to be log. We're going to trace the letter b first. Then we're going to come over and pick up the answer. That's called our argument. Then we're going to go hit our exponent last. So this is the form that will always, always, always be in our parent equation. Log, whatever your base is, of y equals x. And it's very, very confusing, I realize, but just trust that the log is the inverse of the exponentials. Okay? Trace the L if you're going to log, trace the E if you're going to exponential, and everything will work out just fine. Okay? So what I'm going to do now is I want to flip-flop. Let's see. How do we kind of use this? Okay? Right here is problem 3. This is important. We have a problem here, and logarithms are used as inverses, again, of exponential functions. The last problem we're going to do here. And what we have is a situation here. We have a Richter scale for using the earthquake. And the reason we use logarithms is because the Richter scale measures the waves of the ground when the earth is shaking, so an earthquake. So think of the earth shaking as an exponential function that causes the ground to move, and what they're doing is they want to figure out what exponential function caused the ground to move, so that's where logarithms come into effect. Okay, so we're going backwards to find out the source. Alright, so an earthquake's magnitude m, there's the magnitude, is determined by this equation. Notice there's that log, which is this button log on your calculator. I divided by I naught. Remember, anytime you see a subscript 0, that means the initial. I is the intensity of a seismograph reading, and I naught is the intensity of a standard earthquake. And they're giving us this number. That's always I naught. So that's the standard for that problem, for all problems in general. And I don't know where that number exactly came from. A lot of data went into that. But write an equation model. This is going to be m equals, we're just going to trace this, log of some input divided by some initial input of 10 to the negative 4. And we can type all this directly in the calculator. So let the calculator do the work. An earthquake in California measured 6.8 on the Richter scale. That means that is its magnitude. This is its m number. While an earthquake in Japan measured 7.2. How many times more intense was this? So what we're going to do is we're going to figure out the answers, and then we're going to get how many times more intense. We'll divide them and find out, because division is the inverse of times. So let's see. For California, the equation is going to be 6.8 equals log of I divided by 10 to the negative 4 power. And it's very, very important here. I would, again, take this and put it to the other side, 6.8. And now we don't have to worry about this. And we can kind of trace how we rewrite this. Whenever we have an input for log, you need to know that the logarithm, if there is no base written, then it's naturally a base 10. That's important. Keep that in remember that log is always going to be base 10. Now before we had log base 2 because they gave you a specific base. Now they are not giving us a specific base, so this is going to always be in base 10 if it's not there. So what we'll do is we will rewrite this, all right, because we have an unknown input here. We can't just go to the calculator and say, hey, log, hit log, and then put an unknown number there. We just can't do it. We have to figure out what that unknown number is. But what we'll do is we'll kind of use exponents. because exponents will help us figure that out. So how do we write this as an exponential function? Well, we start at the base. Here's our base. We're going to trace the e, and we're going to rewrite this as 10 to the 6.8 power equals I divided by 10 to the negative 4th power. And now this is super easy to do on the calculator, because we just type in these numbers. So let's see. What is 10 to the 6.8 power? Well, get your calculator and go 10. Raise it to the 6. Alright, but think of that number as this. So what this turns into is 6309570.445 equals I over 10 to the negative 4. So how do we solve this now? Well, this 10 to the negative 4 is just a number. It's being divided by I. Or sorry, the other way around. I is being divided by 10 to the negative 4 power. So how do we undo division to get I by itself? Because this is a number. It's no different than 5 or 4 or 10,000. It's just a number. So what we're going to do is we're going to move it to the other side. So if it's being divided, the inverse of division is multiply. So we're going to times by 10 to the negative 4 power. And this, right here, becomes the value of that intensity of the earthquake. So this I becomes 630.9, let's say 6, in California. We're going to do the exact same thing for Japan. I'll do Japan in blue. However, Japan's 7.2, so we're going to write 7.2 equals log of I divided by 10 to the negative 4 power. And since this is a log, I'm going to put this 7.2 on the other side. And I have to remember log is always base 10. So now I'm going to write it exponential so I can solve. So 10 to the 7.2 power equals I divided by 10 negative 4. I'm going to type this in the calculator and multiply it by 10 to the negative 4. 2 steps. Not hard at all once you know how to do the inverses. Alright, 10 raised to the 7.2 power equals that number. Now I multiply it by that number times 10, raise it to the negative 4 power. And there becomes my new intensity for Japan. Obviously it's more intense in Japan, but that means it's probably closer to the what they call epicenter. And then we want to know how many more times intense was the Japanese earthquake. Well, Japanese was this number, California was this number, so to find how many times more intense, we divide those numbers. So let's see. 1584.89 divided by 630.96. How many more times intense? Well, I've already got that up there for Japan. Let's go ahead and divide it by, I'm just going to scroll up because I'm kind of lazy. That was the answer that we got for California. So it was 2.5 times more intense. 2.5 times. That's how we got that answer. And that's a standard application for logarithms. Remember, we rewrote it the opposite way to figure out where it was. You can also use the calculator on this. Let's say I want to use the calculator right on this part instead of using the algebra skills. Go to y equals. Clear everything out, and since this is the log, notice we don't have a number on the base, it's 10. You could put log base 10, but you also can just hit the log button, because if you hit log, it automatically knows that you're in base 10. And what we'll do is we'll type in exactly what we see. This will be our x, because we don't know it. X, let's do this, delete, let's do a fraction, 4, close that. And remember, whatever we do, if we have an equation, we can take this answer and move it over. So we're going to say minus the answer of 6.8. And now we're going to figure out when does this equal the x-axis, or y equals 0. So if you look at your graph now, well, let's kind of cheat here. Our answer is going to be way over here at 630. So let's go to our table set, and let's go where it says table start. Let's go to 625, and just go to your table so you can see some numbers. Notice here's negatives. 630, that says these now become positive numbers. I don't know what it is. That looks like it's a negative. This E just means move the decimal to the left. And this is going to be approximately our answer. And I'll show you on the calculator here. Let's go to window, and we want our max window to be, let's say, 700, because our answer is 630. And I want that to go to maybe count by 100, so we can just see a little bit easier. If we graph this, you can kind of see it's below 0, below 0, below 0, below 0, and now it's going to cross over somewhere in that range. Let me just go ahead and make the window a little bit bigger. Instead of 700, let's go to, let's say 1200, just so you can see plenty of space. And somewhere in here, it's going to actually cross the x-axis. There you go. You can see it somewhere in this range. So how do you find that number? Second calc, a 0. Let's see. We're going to go, okay, we're at y is a negative, so we're okay. We're on the left of the answer. We're going to keep going right until y is a positive. Now y is a positive. Hit enter a third time, 630.95, and I think that's exactly what we got here, 630.9. I rounded it to 6, but there's our answer. So you can also use the calculator to solve these. Okay. All right. Find out if you guys feel good with your table. Let's get some practice, I guess, writing some generic ones. What if I asked you to rewrite, don't worry about number 3 here. What if I asked you to rewrite log base 4 of 5 equals x? How would you rewrite that in exponential form? So that's number 1. Number 2, what if I gave you 3 to the x power equals y? How would you rewrite that in logarithm form? Just one quick example. Okay, so try that real quick. Pause the video. All right, hopefully you've tried that. Let's rewrite this. If I'm in logs, I'm going to exponential, so I always start at the base, and I trace my e. So this becomes in exponential form 4 to the x power equals 5. So those are inverses. What about this one? This one's in exponential. I want to go to log. So I want to write the word log. Then I go through the base, so I write that as my base, 3. I go over to the answer, that's called the argument, put that in parentheses, and then I come up to the x, so it's like an L for log, and like an E for exponential. Alright, once you feel confident, come grab the homework page, get to work on that, ask me any questions. I know this is a little confusing to start, but we're going to be doing lots of problems with logs, and it should hopefully make a lot more sense. Alright, see ya.